Hi student, welcome to the lecture. In this lecture we are going to discuss the CFSE and magnetic properties of octahedral complexes. Now in previous lecture we discussed the various distribution of d electron in T2G and EG orbital for various systems, that is D1 to D9 systems, in strong field and weak field also. So in continuation with this previous lecture, in this lecture we are going to discuss what is meant by the CFSE and what are the rules for the distribution of electron in respective T2G and EG orbital for calculation of this CFSE. So let's discuss what is meant by the CFSE. Actually CFSE is nothing but the total energy caused by the splitting of d orbital, and their occupancy by electron is known as a CFSE. So there are equation for the CFSE in strong field, in octahedral complexes also, in strong field and weak field also. So let's discuss first what is meant by the CFSE. That is crystal field stabilization energy. The total decrease in energy caused by splitting of d orbital and their occupancy by electron. Electron is known as a CFSE. So for the calculation of CFSE in octahedral complexes, there is a respective equation. As we know that the octahedral complexes is splits into T2G and EG group, whereas EG having higher energy, whereas T2 is a lowering energy. So according to this distribution of two groups, it will be designed as the CFSE equation. For octahedral, so we can, that is the number of electron in T2G electron T2G orbitals into minus 4 dq plus number of electron in EG orbitals into 6 dq. So here, that is the CFSE for octahedral complexes. Here the number of electron in T2G orbital into minus 4 dq, as we know that the T2G orbital is a lower energy and EG orbital is having a higher energy. So total energy of T2G and EG at the barycenter is 10 dq. So from that equation we can easily calculate the CFSE for various systems from D1 to D9. So let's discuss. Before discussing the CFSE for various systems, there are general rules for the distribution of electron in EG and T2G orbitals. So what are the rules for that? Let's discuss. Distribution of electron in T2G or EG orbital take place by following rules. That is first atomic principle. That is multiplicity. Then third one, there are two cases as if delta means there is a crystal field splitting parameter is greater than pairing energy, then the obviously the energy required to pair the electrode, that is if is means that this is in strong field and there is a pairing energy is much more required, means that it is a here the crystal field splitting parameter is large, so there will be the electron will pair in T2G, and here pairing energy is large, means that electron will enter in EG. So these are the general rules, and according to these rules there is a electron distribution in energy levels. So let's discuss. There is no effect of ligand field, that is strong and weak field, on the distribution of electron. D1, D2, D3 and D8, D9 and D10 systems as hence their CFSE as in strong and weak field. So here, what are the CFSE for strong field and weak field for D4, D5, D6, D7? Let's discuss. That is in strong field. So for D4, D5, D6 and D7 system. So here in strong field ligand, if there is, that is for T2G and EG. So in T2G there will be the how many electron? There will be the 4 electron, because and for EG there is a 0 electron. So here the according to our calculation, according to our CFSE equation, so there is a number of electron in T2G, that is a 4 electrons, so 4 into minus 4 dq plus 0 into 6 dq, as we know that there is a 0 number of electron in T2 EG orbital, so 0 into 0. So the total calculation of this is for T2G here, and for EG there will be the 0 electron, and for T2G 1, 3. Due to strong field ligand, it will be enter into EG. So there will be the 1 paired electron, and the total, that is a dq, 4 into 4, and there is a 1 pairing, so we can write 1 pairing here as like form. For D5 system, if you observe, then here, that is again T2G and EG. As D5 system, there will be the 5 electron in T2G and 0 electron in EG, as the electron is strong field, so it will be directly enter into T2G and EG. So 1, 2, 3. Due to strong field, it will be again enter into T2G. So here that is a 5 electrons. So here, according to our calculation of CFSE, that is 5 electron in T2G, and there is a 4 dq value and 0 electron in EG. So as per our calculated equation, there will be the dq, and here there will be the 2 paired electrons, so that's why we can writing as a 2p, that is 2 paired. So here for D6, that is, as we know that for D6 that is a T2G 6 and EG 0. So here that is 6 into minus 4 dq plus 0 into 6 dq, that is minus 14 dq, 24 dq plus there will be 3 pairing, so 3p. So here likewise for the D7 system, that is T2G6, and there will be 1 electron after fulfillment of these 3 orbital 1, 2, 3, 4, 5, 6, and here the 1 electron is remaining which is entering EG, and according to that equation, as the T2G orbital is number of electron having 6 electrons minus 4 dq plus 1 electron, so into 6 dq. So the calculation that is 6 dq and minus 24 dq, it's 18 dq plus how many pairs electron? Again there will be 3 pairings of 3. That's why, so this is all about how to calculate the CFSE for D4, D5, D6 and D7 systems in strong field complex, in strong field ligand. As we earlier or the previous discussion, as per our previous discussion, we discussed that in strong field complexes actually the ligand will be singly paired. Ligand will be singly paired in T2G, and again the pairing will be start from T2G, doesn't goes into EG. Whereas in weak field complexes, after fulfillment of single electron in T2G, the electron will enter in EG. So this is the effect of ligand, as we discussed earlier that the strong field ligand will do pairing, whereas the weak field ligand will enter into EG, and after the fulfillment of EG orbital, if there is a remaining of electrons and the remaining electron will be entering again T2G, and the pairing will be start according to number of electron of D orbital. So let's discuss the same system, that is D4, D5, D6 and D7 systems in weak field complexes. Now in weak field for D4, as we know that for D4 system, that is T2G, again T2G and EG, and this we can see in octahedral field. So here that is D4 system, that is 3 electron in T2G and 1 electron in EG, because the ligand is weak field. So the distribution for T2G, that is 1, 2, 3, and for EG that is 1. So according to the CFSE equation, the number of electrons in T2G, that is 3 into 4 dq plus that is 1 electron in EG, so that is 6 dq. So here the total electron is dq, and for 1 there is a 6 dq. So the CFSE for that is 6 dq. And pairing, there will be no pairing, so we cannot write the paired electron. So just it is the CFSE for D4 system is minus 6 dq for D4 system in weak field complexes or weak field ligand. Now for D5 system, the T2G will be 3 and EG will be 2. So the box, according to that box diagram, it will be 1, 2, 3, and for EG there will be 2 electrons. So for CFSE, that is 3 into 4 dq plus that is 2 into 6 dq 12 dq plus minus 12 dq, that is 0 dq. So there will be for D6 system, that is T2g 4 and Eg, that will be the 2. So how it will be distributed? Let's see, 1 2 3 for T2g, 2 electron, 1 2 3 in T2g and 2 electron in Eg, 1 electron again in the T2g orbital. So the number of electron, that is 4 electron in T2g orbital, and there will be the 2 electron in, so there will be the minus 4 dq, and there will be pairing 1. Here there will be no pairing, so we cannot write, but here there will be pairing, so we can write the 1p, that is a pairing. And for D7 system we can write again, that is T2g 5 and Eg 2, and according to that equation, that is 4 dq plus 2 into 6 dq, sorry, there will be the 5 electron in T2g, so there will be 12 dq, and the total electron, that is total energy, that is dq plus there will be how much pairing is there. So here the pairing for D7 system is 1 2 3 4 5 6 and 7. So there will be 2 pairs, so 2p. So this is all about the distribution of the CFSE of respective ions for D4, D5, D6, D7 systems in strong field and weak field. Now let us discuss what is meant by the paramagnetic and diamagnetic behavior of the complexes. So what is meant by paramagnetic and diamagnetic behavior of the complexes? The presence of unpaired electron, is known as a paramagnetism. Whereas the presence of or the absence of unpaired electron is known as diamagnetic behavior of complexes. Diamagnetic behavior can be calculated by the Bohr formula or spin formula, that is S root n in bracket n plus 2, where mu s is Bohr, so that is mu s is a magnetic moment, that is Bohr magneton. And n is a number of unpaired electron. So here, as we know that earlier, as per our earlier discussion, there will be the number of unpaired electron is equal to approximately the Bohr magneton or the magnetic moment of the respective complexes.